Okay, hi everyone. My name is Upal Mahbub, and I serve as the chair of the IEEE San Diego section as well as the IEEE Computer Society San Diego chapter. Welcome to the third talk of our 2025 invited seminar series. Today's virtual talk is co-hosted by the Computer Society chapters of Santa Clara Valley, San Antonio, San Fernando Valley, and Pelus. As always, we have Open Research Institute Incorporation as our media partner for the entire series. I'm delighted to welcome Yash Bhalgat, a final year PhD student at the University of Oxford's Visual Geometry Group, and also a former colleague of mine at Qualcomm. Yash's research focuses on 3D computer vision and machine learning. He is supervised by world-famous experts, Professor Andrew Zisserman, Professor Andrea Vedaldi, Professor Joao Henriques, and Professor Laina. Before pursuing his PhD, Yash was a senior researcher at Qualcomm AI Research in San Diego, where he developed efficient deep learning algorithms for computer vision applications. He holds a master's degree in computer science from the University of Michigan and a bachelor's degree in electrical engineering from IIT Bombay. Today, Yash will present his research on uh, from video to virtual object-centric 3D scene understanding from videos, discussing innovative methods for capturing 3D data using unconstrained videos and incorporating epipolar geometry priors in multi-view transformer models. His current research interests include geometry-aware transformers, neural rendering, and vision language model. So with that, without any further ado, Yash, the floor is yours.
Thank you, Upul, for the very nice introduction. I see some of my previous colleagues on this call, so very nice to be here. Pleasure to be giving a talk to all of you about my recent research in 3D vision understanding. So I'll just share my screen first, and I have one slide about self-introduction, but I think Upul basically covered everything, so I can quickly move on to the actual contents of the presentation. Okay, just to confirm if you can see my slides.
Yeah, we can.
Okay, all right. So yeah, a little bit of again repetition of what Upal said. I'm doing my PhD now, my final year at Oxford, working with the Visual Geometry Group. I'm advised by Professors Andrew Zisserman, Andrea Vedaldi, Joao, and Iro. I've worked at Qualcomm from 2019 to 2021 with Jamie, who was on the call I saw, and Fatih from the Perception team. I also worked with Upal on the XR projects when I was there. Since I am in Oxford, I have been focused on 3D scene understanding from videos on object level. So I will talk about various works today, specifically focusing on 3 papers I published in the last few years. The first one will be about 3D object segmentation in 3D in unconstrained scenes. The second paper will be about incorporating multi-view geometry priors into transformers for a specific task of image retrieval. And lastly, I will talk about a very recent work I presented at ECCV about, again, object segmentation, but this time I will talk about how to do that using language queries in 3D scenes. So this paper is called Nested Neural Feature Fields. I will go into the depth when I reach that point. And I will also talk about a few other published and ongoing works if we have time towards the end of the presentation. My goal is to give about 15 minutes for each of these 3 papers, and we can have questions in between after every paper, so we can talk about the paper in more detail. And towards the end, if we have time, as I said, we can go over some remaining works from my PhD. All right, let's get started. So the first work is about object segmentation in 3D, and the usual approaches for obtaining 3D data, use LiDAR, structured light cameras, time of flight cameras, and so on. But these are very specialized equipments, and they're usually quite complex. And the main problem is they're not scalable. So we don't have large-scale 3D annotated data to train these models for object segmentation. On the other hand, videos are also a rich source of 3D information because they capture the same scene from multiple viewpoints. So they give us multi-view information about the scenes. They are quite easy to record. We have millions of videos out there on YouTube or other websites, and they serve as a common source for both static and dynamic information in scenes. So if you have an apartment and if you just scan the apartment using your phone camera, you have pretty much a static scene. But if you have, let's say, a traffic camera on the road, or you have some moving camera on the road, you have a dynamic scene where cars are moving but the buildings and the roads are static. So videos serve as a common source for both static and dynamic information, as well as being very easy to record. So that gives us a very good source of data to train these models or inference on these models. And in this work, the focus was to start from a video of a scene. As I said, let's say you scan an apartment using your phone camera. We can go from that video to a 3D representation of the scene. So you can use a coal map to get an SFM point cloud, or you can use a NERF model, or you can use Gaussian splatting, which is quite popular nowadays. So going from here to here is not that difficult. But the next step is to go from the 3D representation to an object level reconstruction of the scene. So you want to identify the scene at an object level, both semantic and instance level reconstruction. So you want to identify all the chairs, all the tables in the scene, but you also want to distinguish between different chairs in the scene on a 3D level. So that was the goal of this work, to go from a monocular video to an object level panoptic reconstruction of the scene. As I said before, data is a big problem here. So you can't really train a feed-forward model to do 3D segmentation. Most of the models out there, like YOLO 3D and all, like other models, don't really generalize very well to unconstrained scenes. Now, an alternative to that problem is to rely on 2D segmentation models. Let's say you take SAM, which has been trained on millions of examples of segmentation data. SAM performs quite well on most 2D images. Now the question is, can we leverage these large-scale 2D foundation models or 2D segmentation models to perform object segmentation in 3D? And that's what we address in this paper. So the idea is, as I said, we start from a video of the scene. We reconstruct the scene from the video using NERF or Gaussian splatting. In parallel, we also run a 2D segmentation model on the scene. So that segmentation model will give us semantic segmentations and instant segmentations of the scene. Now I will come to the problems like faced in these segmentations in a moment. But the idea is to take this 3D reconstruction and the 2D segmentations and lift them into 3D to obtain this 3D reconstruction of the scene. So we call this approach contrastive lift, and I will now describe why we have such a name for this approach. So one problem we have with these 2D segmentations is they are, not very multi-view consistent. If you look at the semantic segmentations of the scene, they are more multi-view consistent because a chair will be a chair from any viewpoint you look at it, right? So they are, in theory, multi-view consistent, but in practice, you have lots of noise. So you can see that the floor is being segmented as different things in every different frames. The chair is a chair in every frame, but there is some segmentation noise. So the segments are not accurate and multi-view consistent in all the frames throughout the video. But if you look at on the instant segmentation side, the problem is even more severe. So if you don't run any tracking on the video, the instance IDs for every object is going to be completely different in every frame because we have obtained these instance segmentations independently for each frame. So as you can see, this chair has a different color, which means a different ID in each frame. And that's because we did not run any tracking on the video. So these are definitely not multi-view consistent. And the question is, can we take this information, which is multi-view inconsistent, and still perform 3D segmentation using that? And that's where we come to the contrastive approach of this in this idea. So what we say is that let's look at a single view of the scene, and if we select 4 pixels in this scene, in this image, we can see that these 2 pixels are of the same object because in a single image there is no question of multi-view consistency, right? And these 2 pixels are of the same mask, so they have to be the same object. So in a single image, we know if given 2 pixels, u and u prime will be from the same mask or not. So what we propose here is to learn an embedding field where the embeddings of 2 pixels from the same mask are pulled together and embeddings from the pixels of two different masks are pushed apart. So we have this push-pull formulation where the embeddings of these two pixels are pulled together and these two pixels are pushed apart. And that gives rise to a contrastive formulation where we have this energy function that that pushes and pulls embeddings based on their underlying 2D level masks in every frame. And the idea is that this works because if we have, let's say, these two pixels in two different views, now you can see just manually that they are probably the same pixel, like they correspond to the same 3D point in the scene, and let's say that's this point, right? So we learn this embedding field in 3D. So we define this embedding field in 3D for every 3D point in the scene. And the way we obtain the pixel level embeddings is by rendering these 3D embeddings into 2D. So basically, previously when I said that we have an embedding for every pixel, these embeddings are obtained by rendering a 3D embedding field, which we are going to optimize. And if, in theory, we are able to optimize that 3D embedding field, we can see that these two pixels, if they correspond to the same 3D point, they will have the same embedding because it is rendered from the same 3D point. So we have this multi-view consistency in the embeddings on 2D level kind of hard-coded in the way we represent this scene. Now the question is, how do we optimize this 3D embedding field, given this 2D level data that we have that I described before? And so we propose a NERF kind of framework. First, what we do is we take the image, multi-view images of the scene, and we optimize a NERF model. A NERF, if you're not familiar, is short for neural radiance fields. What it does is it takes a 3D query point, and for that query point, the NERF model predicts a color and a density. And then what we do is we take all the colors and densities for the points in 3D and we render them back into 2D colors. And we compare the 2D rendered colors to the ground truth 2D colors that we have from the data we have using a photometric loss, and that's how we optimize the NERF model. So towards the end of the training, if we query any 3D point using this NERF model, we should get the true 3D color and the true density of that point in 3D. So what we do is we first optimize this NERF model independently, and then we extend this NERF model to add one more output, which we call the point embedding. So as I said before, we have a 3D embedding field, and that's basically this field. So for any 3D point, in addition to the color and density, we also predict a n-dimensional embedding, which is, by the way, unconstrained. Like right now, when we start the training, we have no idea what these embeddings are, but by optimizing a contrast and loss, eventually we will get embeddings such that different objects will have a different embedding in the embedding space. And the way we do this is we query the 3D, the NERF model for every 3D point. We get 3D embeddings. We render them in the same way we render the colors. So we get 2D pixel level embeddings. And now we have a push-pull loss on the image level. So what we do here is we go through every image in the scene. We sample a few pixels randomly. Let's say, as I showed before, we sample these 4 pixels in this given viewpoint, and we look at the embeddings that are rendered for these 4 pixels, and we apply a contrastive push-pull loss on those pixels. So what will happen is, towards the end of the training, the pixels that correspond to the embeddings that correspond to all these pixels of this mask will all be clustered in some part of the embedding space, and the embeddings that correspond to this object will be clustered in a different part of the embedding space. So we will obtain these different clusters that correspond to different objects in the scene. And then if we perform some post-processing clustering algorithm, we can extract the objects from this embedding space at the end of the training. Now, this approach works very well. So if we just train this model as it is, it actually gives us good performance. But what I observed is that this vanilla contrastive learning approach has some instability. So it does not always converge very fast. It takes a long time to converge, and there can be sometimes exploding gradients which we have to deal with. So for that matter, I propose this slow fast NERF approach. So this is inspired by all these Dino kind of frameworks where you have a teacher network and you have a student network, and the student network weights are coming from an exponential moving average of the teacher network. So in this case, what I call them is a fast nerve and a slow nerve. And the slow nerve weights are purely exponential moving average of the fast nerve weight. So there is no gradient descent happening in this branch of the network. The gradients are only propagated in this branch of the network. And what this achieves is the slow nerve actually leads to more stable embeddings, and that leads to a more stable kind of gradient learning approach in the training regime. We also have a concentration loss, which basically says that you obtain these pseudo centroids using the slow network, and you enforce the fast embeddings to cluster around the slow centroids that you obtained. And this gives to more focused clusters at the end that gives to more high quality performance, as I will show you in a moment in the results. So this is the main framework or the main architecture of the model. And we evaluate this on the usual ScanNet and all these benchmarks. But I also created my own benchmark for this paper called Messy Rooms. And the name is quite meaningful because the rooms are actually quite messy. So what I do is I use a synthetic data generator and I drop objects in a scene. So they are all like physically, realistically placed in a scene. And we have about 500 objects per scene. So there's heavy occlusion, there's lots of cluttering happening. So it's a very difficult problem when we try to segment these objects. And the goal is to see how well the model can scale with the number of objects in the scene. So we start from 25 objects per scene and we go up to 500 objects per scene, and we see how the model scales. So here's an example of how it looks like. So we start from a video, as I said before. We have the 2D level segmentations, which are very inconsistent. And at the end, we have these highly consistent segmentations, which we obtained from our contrastive lift approach. So as you can see here, the segments are very 3D consistent because every pixel is corresponding to a purely 3D point. And if you look at different views, we also can segment through occlusions and obtain accurate segmentations. Here are some results and some comparisons with previous works. There's a paper called Panoptic Lifting, which does the same thing that we do, but they use Hungarian algorithm for performing the matching. Instead, we use a contrastive algorithm for the matching. The problem with the Hungarian matching is it is constrained by the number of objects it can segment. So you have to provide an upper bound for the number of objects in the scene, but in a real life scenario, we might not know an upper bound of the number of objects in the scene. So if you provide a bound of 25 objects and the scene indeed has 50 objects, the Hungarian algorithm will actually not work very well. But our algorithm does not have such a constraint, so it works quite well on all real life scenarios. We also have better performance. So some occasions where it's quite difficult to segment objects, we get a slightly better performance. But to be honest, it's more about how real, how practical the approach is for real life settings. I have some more numbers, but I won't waste too much time on this. Basically saying that our approach works even if we don't have that slow fast method. It still works, but if we have a slow fast kind of method, it gives us even better performance in terms of the panoptic quality of the segmentations. All right, I'm going to skip this. This is visualization of the centroids. So as I said, we form these clusters in the embedding space, and we can look at the distances of different pixels, pixel embeddings from the corresponding centroids. And as you can see, we have very crisp sort of clusters because if we take the centroid number 1, the pixels which are on the sofa only have a very high similarity, and all the other pixels have a very low similarity, as you can see here. Now, the same thing can be observed in the Messy Rooms dataset. And what I want to really show here is, if you look at the last centroid, centroid number 4, you can see that this object is heavily occluded in this case, and you can still get a very good segmentation of that object, even under heavy occlusion. So let me see how much time we have. Okay, we have 15 minutes passed on this paper. So basically, the main kind of idea here is we are not constrained by the number of objects in the scene. The embeddings that we learn are grounded in 3D by design. So we have a 3D consistent embedding field that we optimize here. And as a byproduct, as I showed before, we also have higher quality 2D instance segmentation. So actually, if you start with a low quality 2D segmentation model, like Max Former, for example, is not very good at segmenting objects. If you start from that, our model can actually improve the 2D level segmentations even. So it also has that ability to improve like 2D segmentations. We have a new benchmark called Messy Rooms, which you can look at. It's completely open sourced. The only problem is this approach works only for static scenes. It does not work if the scene has dynamic objects, and it definitely relies on accurate geometry reconstruction. So let's say if you don't have enough views of the scene, then you won't get a good geometry, and that might be a problem for this approach. So these are some limitations of this current approach. Okay, let's take a small pause here. If you have any questions, I can answer that before moving on to the next paper. Any questions?
The renderers in your image, are there different renderers for different types?
No, actually. So the renderer is not a learnable module. So it doesn't really. It's the same renderer, but yeah, with no learnable parameters.
Hi, Yash.
Yes.
Yeah, very nice to see your congratulations for the great work. And I'm
Yeah,
just
good to see you.
wondering, yeah, great to see you. Yeah, and I'm just wondering, besides the constructed loss, there might be other like adjacent techniques that you can further refine to, let's say, to further push forward the the different object of the embedding, right? And then push closer to the same object of the embedding. For example, like widening to kind of remove the covariance matrix of the off-diagonal items, and then also boost the diagonal items, something like that. That might work as a supplementary technique.
Absolutely. That's actually a good point. So contrast field loss is not the only loss which can achieve this. As you said, there are better variations of this. In our paper, we do compare with other variations, and we observed like not much difference in the performance when we use these different variations. But I think there have been some follow-up works after my paper. Like some other people have done solve this problem, and they have seemed to achieve even better performance by using different loss functions. So I think you're right. Like definitely possible to push this further.
Yeah, but otherwise this is really a good breakthrough for your work.
Thank you.
Yeah, thank you.
All right. If there are no more questions, we can talk about the other paper from CVPR 2023. This was actually my first paper from the PhD, and it was about teaching transformers multi-view geometry. So it sounds very fancy, but the idea is that transformers have been very well at vision tasks, and this is a figure from the Dino paper. So it shows that transformers using self-supervised learning can learn really good features which can have incredible downstream applications. And the issue is though that these transformers don't have enough inductive biases in the training itself, and more specifically, they don't really understand 3D geometry as has been shown by various works before my paper came out. And then we thought about can we actually incorporate what we have in the 3D networks into this 2D level transformers. So basically, our world is inherently 3D, as I have talked about before, and there are some specific laws of projective geometry that all the images obey. So the images that we capture follow some very specific camera models, and that kind of enforces specific projective geometry rules on the images. And these actually are very important priors that should be learned by networks to be more robust for downstream tasks. And the problem is that there's almost near infinite variety of how many variations you can have in this projective geometry rules, right? But the good thing is transformers are very good at scaling to large amount of data. So if we do indeed have a near infinite variety of variations in this projective kind of transformations, we can hope that transformers can learn these variations and incorporate those visual priors into the layers of the network. So that's the question we address in this paper, is that can we keep this scalability of vision transformers, but at the same time, can we add geometric priors for robustness to downstream tasks? And specifically, we look at a task of image retrieval. The idea is that given a single image of an object, can we retrieve all the other images of the same object? So this is a very instance level task. It's a very fine-grained recognition task. And you can imagine that you can have a database of millions of objects, and you can have very similar objects in the database. Let's say you are looking at this teddy bear from one angle. The database can have 1,000 other teddy bears in the retrieval set, but you only want that specific teddy bear that is being queried by your query image. So it's a very fine-grained task. There can be a lot of pose variations. You can have other images of the teddy bear from a very extreme pose, relative pose, but you still want to retrieve that image. So the question is, how do we do that? Because the current vision transformer models don't generalize well to large pose variations, and they can get confused very easily if you don't have enough overlap in two given images. The idea we propose here is to use epipolar geometry and incorporate that kind of prior into the transformers. Just to give a very basic background about epipolar geometry, is that if you have two images of a scene, let's say image one, image left and image right, and you have a pixel XL in the image, in the left image. Now this pixel XL can have almost infinite corresponding points in 3D if you don't have any other viewpoint, right? So if you draw a ray from the camera origin passing through the pixel XL, it can basically correspond to any of these points, X1, X2, X3 in 3D. And then if you project all these possible 3D points back into the other viewpoint, you get this line here. So basically what this says is, if you only have these two views of the scene, every pixel in the left scene will have a corresponding line in the other scene. So all these pixels on this line could be a potential matching point for this pixel here. So, and this line is called an epipolar line of this corresponding pixel. So every pixel here will have a corresponding epipolar line here, and every pixel here will have a corresponding epipolar line here in this image. In fact, if you think about this a bit more, all the lines actually have an exact match. So basically what this means is, if I take any pixel on this line and try to find the epipolar line in this image, that line will pass through this pixel. So what I'm trying to say is, there is a one-to-one correspondence between the epipolar lines in these two images, and we will use this fact in our approach in this method. All right, so as I said before, if you have some query points, I don't know if you can see this, but there are very faint points I have marked here in the left image. And what I'm showing is, on the right, if I have this, capture the same scene from different viewpoints, you can see how the epipolar lines change for the same pixel. So let's say this green pixel has this corresponding epipolar line, but it is kind of changing its orientation in every image you capture of the scene. That's just to understand like how this look like in real world. And the question is, can we enforce or use this geometry to train the transformers to look at only the points which are relevant in the search process? What I mean by this is, if you look at the attention mechanism in a transformer, you're kind of trying to perform a search process, right? So for every point in the every pixel in the first image, when you perform cross attention, you're looking at all the other pixels in the other image and trying to find which pixel attends the best to the current pixel. But if you want to really have a geometrically inspired attention map, then you only want to look at the pixels on the epipolar line of the corresponding pixel. So what we do is we enforce this epipolar kind of constraint on the attention maps in the transformer model, and we see that this actually leads to much better performance in a downstream task which requires 3D understanding. So we propose this light touch approach, which basically means that we start from a vanilla approach where you don't have any geometry kind of based thing. So basically you take an image pair, you pass that image pair through a CNN to obtain some features. You transform that feature map into a sequence, which you pass through a transformer. That transformer is supposed to give you a score which says if the two images correspond to the same object or not. So it's a 0-1 score, which is optimized using a binary cross-interval loss. Now, the question is, like, can we augment this transformer to become more multi-view geometry aware? And that's what we do using this epipolar loss here. What we exactly do is, at training time only, we assume that we have the camera poses for these two images. Actually, even though if you don't have the camera poses, you can easily obtain them using any off-the-shelf kind of pixel matching approach. And I will show later that it doesn't matter, how accurate that pixel matching approach is. Even if you have a very weak kind of a model for that, it still works. Like, if it basically says that if your attention maps, if your epipolar geometry is noisy, that is not a big problem for this approach. So basically, you obtain this epipolar lines using the camera poses by solving this fundamental matrix equation, and then you rasterize those lines into these binary maps that we have here. So as I said before, every line in the first image will have a corresponding line in the other image. So we take this 7x7 grid, because we have a 7x7 map here, and we obtain one line for every pixel in this 7x7 map. So we basically have a 7x7 grid here, and each of these grids is 7x7. So we actually have 7 cross 7 cross 7 cross 7. So we have a 4D kind of matrix, which is binary. It is 1 when we have a epipolar line, and it is 0 when we don't have a epipolar line in that grid. Now we use this binary map as the ground truth for the cross attention matrix in the penultimate layers of the transformer. So what we are basically saying is the transformer in the last layers should only attend on these kind of epipolar guides that are obtained for these particular image pair that we have here. And when we train this model using this epipolar loss, I will show you in 1 second here. In test time, when we don't even have a camera pose as input or any geometry as input, the transformer has learned to predict the underlying epipolar geometry of this input pair in its cross-attention maps, and it then uses this epipolar geometry to perform the predictions for the downstream task. So we call this to be epipolar aware or geometry aware transformer, because without any camera pose or geometry inputs, it can infer the geometry just given the image, the input image pair that we have here. So that's basically the kind of the gist of the approach. And we also have one more variation called a max epipolar loss. So what this basically does is, as I said before, for a corresponding pixel, we can have any pixel on this line which can match that pixel, right? So if I go back here, for this given pixel, any pixel on this line could be a matching pixel. But what if we can find that exact matching pixel given the true geometry of the scene? So we actually can do that, and we have a loss called a max epipolar loss. So what we really do here is we say that we are not going to optimize the cross-attention maps on every pixel that we have, but we are going to take the maximum attention value for the given image pair and only optimize that attention value to be high for the given epipolar geometry of the input pair, image pair. And when we do this, initially when the training starts, actually these attention maps are completely random. So they actually are very meaningless. So when you take the max of the attention values, it will just give you some random point on the image. So it's going to be completely meaningless. But we observe that as you train the model, the attention maps become more and more sparse. So the maximum of the attention values kind of drifts towards the true 3D aware matching pixel given the downstream task that we have at hand. And I have some visualizations for this. So let me just move on to the visuals in one moment. So let's say you have this image pair. Now, this image pair was never seen during training. We did not even have this class during training. So microwaves were not included in the training data. And this is the actual ground truth epipolar guides that we have that we compute using the ground truth data. But these are not passed as input to the model. So the model has no idea about this ground truth epipolar geometry. But as I said before, if you train the model with the epipolar loss, it can predict the underlying geometry just within the cross-attention maps, and you can see that this matches the actual geometry very closely, which is quite interesting to see. And if you train the model with our variation, which is the max epipolar loss, you can see that the attention maps are more sparse. So if you actually overlay these attention maps on the image, you can see that the maximum value of the attention maps actually overlap with the true matching point. So basically, if I take, let's say, this corner of the microwave, and the corresponding point, let's say, was this one here. So the attention maps here will actually show that. So the attention map corresponding to this pixel will have a max value at this pixel during the testing that we have observed in our model. And just to show you some results, so as I said, we were evaluating this model for image retrieval. So we developed our own benchmark called Co3D Retrieve. So Co3D is a data set from Meta, which has about 1 million objects and a round table videos for the objects. So we create a benchmark where for every object we have 5 views. So these 5 views are taken at equally distant camera parameters. And what we define a task to be is, given any of these views, we want to retrieve all the other views of the image of the object from the database. And as I said, there could be thousands of other teddy bears, and we only want this specific object from the database. And let me show you some interesting results here. You can see here that the query image is of a sofa. And if you just perform a simple retrieval approach, it will only retrieve the closest sofa image, and then it will just retrieve some random chairs from the database, because it doesn't really work well for all the other extreme pose variations. Then we look at an approach called RRT, which is short for re-ranking transformers. So it's a re-ranking approach where you perform global retrieval first, so you get all the top K retrievals, and then you perform a re-ranking within those top 100 or top K retrievals to get the best possible kind of shuffling of the retrieved objects. And this actually improves the performance. So it does retrieve another image of the same sofa from a different pose, but it cannot retrieve the remaining 2 images that we can retrieve in our approach. So as you can see, our method can retrieve all 4 images as the top 4 retrievals. And surprisingly, the last image, as you can see here, is actually at a very extreme pose variation. So it's almost like 180 degrees variation in this pose here. And it can still determine that it's the same object that we have queried here. I also have a funny example here. Can you spot what's wrong with this image here? So it's marked in red because it's not the correct retrieved object. Can someone tell me what is wrong with this retrieved object given this query?
Yeah, there are 2 cars here, right?
Yeah,
Direction.
exactly.
Yeah.
Direction, yes, but actually it's actually not the same train, because you have 2 cars here, which is a very minute kind of difference. And our approach can sort of deal with that. So as you can see here, the top 4 retrievals are of the correct approach, and it did get the wrong approach, the wrong car as the 5th retrieval. But that's because we only had 4 other images of the same object. But if you did not have this geometry kind of understanding, it's very hard to identify this this fine-grained difference within the query image and this retrieved image that we have here. So yeah, we have all these results here, but the main takeaway from the paper was you could distill this epipolar geometry into the transformer, the models that we have, and you only need this ground truth or pseudo ground truth information at training time, but in inference time you don't need any pose information or any 3D information for inference. And you can even think that this implicit sort of training approach could be extended to even more problems. Like, for example, if you want to incorporate physics laws into the transformer approaches, let's say you are doing some dynamic sort of modeling, maybe you can do the same sort of implicit training where you have ground truth physics during training time, but during inference time you don't have any ground truth physics model, but the transformer itself infers the physics in the scene and makes more realistic or more robust predictions of that particular task that we have at hand. So this was the main takeaway here, and kind of I could go over the results, but I didn't want to waste time on the actual numbers because in the end I think the approach is what matters, and the numbers are just for papers. So if you have any questions, we can have them here. We have sufficient time to go over the last paper. So any questions? Okay, if there are no questions, we can move on to the next paper. This is the last paper in today's talk, and if we have time left at the end, I can talk about a few ongoing interesting research papers we are working on right now. So we talked about this problem of 3D object segmentation before, called contrastive lift. And in this paper, we address somewhat a similar problem. So we still want to segment 3D objects, but we want to do it using language, because language can be a very useful tool, a very general tool to understand scenes. And the open vocabulary kind of approach gives us more general kind of solutions, because let's say in contrastive lift, we might be limited to a specific number of classes that we have in the scene. But if we have an open vocabulary approach, we can deal with any number of classes or any kind of semantic level of classes. One more thing we want to talk about here is hierarchical understanding of the scene, because in a scene you can have objects, you can have parts of objects, and you can have parts of objects, right? So if I have this bottle here, this bottle has a cap, it has other things on the body of the object. So what if we want to segment the scene at these different hierarchical levels? And previous papers on this topic did not really address the hierarchical aspect of 3D understanding. They were simply addressing this straightforward kind of open vocabulary segmentation. But in this work, we actually deal with different hierarchies in a 3D scene. So to give a flavor of what we are going to look at is, let's say you have an input scene, which is basically a bunch of images of the scene, and we can reconstruct the scene into a 3D kind of representation. So here I'm showing you a Gaussian splatting kind of rendering of this input scene. And you want to query the scene using some language query. So let's say you have a query called toy chair. So you expect the model to give you these two chairs as the segmentation output of the model, right? But what if you go a bit more specific and you say, I want the red toy chair? So you expect the model to give you only that red toy chair and not to give you the green toy chair, right? Similarly, if you say a green toy chair, you expect the model to give you the green toy chair and not the red toy chair, and so on. Lastly, if you say a chair leg, which is asking only for the legs of the chair, you expect the model to only give you the legs of the chair and nothing else, right? So this is what we can achieve with our model. So we can go hierarchically deeper into different attributes of the given query and get the corresponding segmentations of the objects that are queried for. Just as a context here, as I said before, a scene can have multiple levels of abstraction. You can think of a scene as just the layout. If you can go further and think of the semantics of the objects, you can go even further, like I talked about in the previous paper, where you can think about the instance level separation of objects. And you can go even further to think about the relationship between objects. You can say that I have this donut, but I have this chocolate donut or a blueberry donut. Or as I showed before, you can have a chair, or you can go deeper and you have a green chair or a red chair. So this is sort of a semantic hierarchy that you can have in a scene. You can also have object relationships. So you can say a donut, or you can ask for the donuts in a box. So you're asking for this very specific donuts that are placed inside a box. So there is a spatial relationship between a box and the donuts in the scene. You can also have a query such as a cup or a bottle, and you can have a very specific query to give you the lid of the cup or the lid of the bottle, right? So there can be multiple lids in the scene, but you want that specific lid which is of the cup or the bottle. Okay, so that's what we try to solve in this paper, where we ask the question that, can we use language as a tool for this hierarchical 3D understanding of the scene? Okay, the main ideas here is the most existing works, such as there's a paper called LERF, which stands for Language Embedded Radiance Fields. And these papers previously only used CLIP to distill language awareness in 3D. And the problem with using CLIP is it is not very good with compositional queries. For example, if you query a paper napkin with CLIP, it detects paper and napkin as separate concepts, but you actually want the paper napkin. You don't want any paper or any napkin in the scene, but that's what CLIP does. Similar behavior with partitive expressions, where you have bag of cookies. In this case, you want that specific bag which contains cookies, but if you just use CLIP, CLIP will look at this and think of a bag, so it will segment all the bags, and it might segment all the cookies in the scene. So it kind of jumbles up the entities that are present in the phrase. So it's, as I said, not very good with compositional queries where we have different entities and we want to understand the relationship of these entities in the query. Secondly, efficiency. So most previous approaches for hierarchical understanding are extremely slow. So a LERF, would evaluate a scene at multiple scales. Like example, 30 scales for every given query, which might take 10 seconds for getting the inference, which is just not practical at all. And the computation can be very badly like linearly scaling with the number of granularities. So if you have 100 scales, it can take even more time to generate the inference. In our case, though, we can actually run inference at almost 1 second per query, or if we have even less scales, we can go up to 0.1 seconds per query, which is about 100 times faster than what the previous approach could do. The main idea is of a nested neural field, as the title of the paper says. So what we do is we learn an embedding field using the NERF model, where different features or different dimensions of the embedding field capture different granularities of the scene. So let's say we have the first 32 dimensions of the feature field. That 32 dimensions should capture a cup level of the scene. But if you add more and more features, it should capture even finer granularities, such as it should capture the lid of a cup, or something even more finer in the scene. So as you go from coarse to fine level, you keep on adding more and more dimensions in the scene, and eventually we have this kind of a nested field, which is a single feature field. So remember that it's not separate vectors for every scale, but a single vector of which different dimensions capture different scales of the scene. And eventually what we can do is we can define or design something called a composite embedding, which can allow us to perform the inference in a single evaluation. So as I said before, previous approaches would need multiple evaluations of the same query, but in our case, we can do this in a single evaluation, which leads to a huge boost in the speed of the approach. The way we do it is we start with a given set of posed images on the lower right of the slide you see here. We optimize a 3D Gaussian spreading model of the scene using that. Parallelly, we also run a SAM, which is the segment anything model, on these posed images. So we get these 2D level segmentation masks, which are again multi-view inconsistent. So we don't need to have multi-view consistency here. And what we do is that we compute something called a scale for every mask. So we project these masks into 3D using the depth we obtain from the 3D Gaussian spreading model, and we compute sort of the largest eigenvalue of the covariance matrix, which reflects how big each mask is in the true 3D scale of the scene. Then what we do is we define a feature field which is modeled by a triplane model. So we actually could have had a feature field per Gaussian, but that just becomes computationally too expensive. So we instead have a triplane where we query each position of the Gaussian to get the feature field here. And then we render them using the splatting model, excuse me, to get the rendered features which are of the size of the image. So we have H cross W cross D features. And what we do is to train the model at multiple scales, we take the scale that we obtained here for each mask, and we only pick those dimensions that correspond to a specific scale. So we have a mapping which takes this scale and it maps it to the number of dimensions we should use at that scale. And we project this subset of the features back to the same dimension. So we use the W matrix, which projects the features back to the same dimension as the clip features, and we have a simple mean squared loss here. So what this does is it takes the features at different scales, which means it takes different subsets of the same feature field, and it optimizes that using the clip features that we obtain for the image level segments that we have here. So the clip kind of brings in the vision language similarity, and eventually we can use that to query the scene using language queries. And we also have, as I said, this composite embedding strategy, which is actually a bit more involved. So I would recommend you all to look at the paper to understand the derivation mathematically, how we obtain this. But in principle, what we are doing is we take a weighted sum of all the possible scale-aware features of that pixel, and we compute this composite embedding for every 3D point in the scene. So what we do is we have this, let's say, theta I from 1 to d, which reflects the different scale-aware features of that corresponding 3D point, and we project that back to the same dimensions of the scene, which we compute the softmax loss with canonical phrases like object, stuff, thing, part. So these are just very general phrases, and we look at the scales which have the highest relevance at every given point and use that as the composite embedding. So we get this kind of holistic view of the scene at all the scales in a single embedding, and we can use that to evaluate the scene, given any query phrase at inference time. This part, I imagine, can be a bit confusing also because I went over a bit quickly over this. But as I said, I would recommend you to look at the paper to really understand how we have obtained these composite embeddings, and how it leads to a very fast inference time speed ups. But let me show you some cool demo here. We have some time left. So this is a scene where we query different objects of the scene in 3D, and we get segmentations here. So for example, we are going to query hat on a rubber duck, and we get the hat on the rubber duck. If we go further, we can look at the chairs, and we can, as I said before, we can query toy chair, or we can query red toy chair and get the specific red toy chair, or we can query the scene for a green toy chair and get the green toy chair, or we can go for the legs, as we will see in a moment. We can query chair leg, and it will give us the legs of the chair as the output of the model. And it is, as you can see, very 3D consistent across different viewpoints. Here we are querying cup, and now we will query lid of a cup. As you can see, it gives us the specific lid of that cup. It does not give us all the other lids. If we query lid of a box, it gives us lid of the other boxes and not the cup. You can go for the donuts. You can query donuts. It will give you all the donuts here. You can go for a very specific query, such as a chocolate donut or a blueberry donut, and it will give you, the specific donuts that you're querying for. Same thing here. Cookies, it will give you the cookies here. But if you say bag of the cookies, it will give you only the bag of the cookies and not the cookies that you had previously segmented. If you say stuffed, it will give you both the stuffed animals. And if you say stuffed bear, it will only give you the stuffed bear and not the other animal here. So that's how it looks like when we inference the model. Okay, so I can talk about the other papers that I have in the pipeline going on right now, but we can also talk about this work in more detail if you have some questions. So any questions about this paper?
Hi, Yash again. Yeah, I think it's very cool work. So I think that's like you apply the hierarchical concept to kind of put more restriction based on the, let's say, to refine the scope of the properties for the matching object, right? And potentially in the language, given the diversity of the language, there could be other reasoning aspect of the language itself.
Yes.
So potentially you might extend this work to other types of relationship to in the logical sense or reasoning sense to kind of
absolutely
for the objects.
And that's a great point, Jamie. I think you kind of read my thoughts here, because this model works for simple queries. If you can say bag of cookies or something like a lid of a cup, it works there. But if you have a more complex query, like if you ask the model to segment the chair in the corner of the room next to the brown bed, if you have such a complex query, then it won't work. And as you said, you might need more kind of reasoning here to break it down into simpler queries and then use the model. There's a paper called LLM Grounder. It's not my paper, but I think it does something like that. It uses an LLM to parse a given query into simpler components and then uses some underlying model like my model to segment those objects. But it's definitely a very cool idea, and I hope that people can do this.
Yeah, very nice. Yeah, thank you, Yash. Yeah, good work.
Thank you. Any other questions?
Best for tonight.
Yes.
Sorry?
Right?
Yeah, I think that was some noise. Yeah.
Okay.
Yeah.
All right.
Yeah,
if
really
we
nice
have
work.
some... Thank you, Gopal. So, do you have some more time, or like what's looking like?
I think you can feel free to continue if you
Okay.
want to hear more about it. Yeah.
Okay, perfect. I just have a couple of more slides. So it's not going to go in as much detail as I went before, but I just want to give you a flavor of what I'm doing apart from these works in just like other collaborations. So I had a paper in ACCV last year called 3D Aware Instance Segmentation and Tracking in Egocentric Videos. And in this paper, I won't go into too much detail, but the problem was egocentric videos are quite difficult, because you have lots of occlusions in these videos, and the camera movement is quite severe because the camera is on the head of the user. So as you know, it can have lots of rapid movements, very little multi-view kind of context of objects. So it's in general a very difficult problem in terms of 3D understanding. And if you think about object tracking, these videos are also quite long. So you can have 1 hour long videos, let's say in Epic Kitchens or Ego 4D datasets. And the issue is, how can you track objects consistently in such long videos? So we address that problem in this paper, where we use a very explicit 3D approach to do this. So we build a 3D model of the scene, of the static parts of the scene. And for the dynamic objects, we propose a very simple sort of a cost matching framework, which uses this 3D reconstruction to guide the tracking of the objects in the long-term videos. And if you go to the paper, you can see that we obtain very good results in tracking. We can track objects in much long-term, even compared to state-of-the-art models like SAM-V2. We can even outperform that model. And interestingly, we can also leverage these models to improve the performance of our method. I had one more paper called Silver, which is a scalable nerf model for large-scale scenes. And let me just cut to the chase and show you a demo of this method. So this is an area in Oxford called the Maths Institute, and it's quite a big area. And as you can see here, we have a very large scale nerf model of the scene, which can give us very high fidelity geometry, as you can see on the right side of the image here. So we have almost like centimeter level accuracy here, which is quite useful for robotics applications. We are actually walking through a big area, as you can see on the top right. It shows us walking in the 3D scene, because we are also running some SLAM pipeline on the back end here. But yeah, this is one paper which we had with the Robotics Institute in Oxford. And I think we also have an interesting data set which we open sourced with this paper, which has a large scale kind of ground truth 3D data to train models at this scale. Apart from that, I have other papers which have been published recently. I had a paper on diffusion models, where we tried to generate reflections in mirrors using various in-painting models. And this was accepted to 3DB and will be presented in March very soon this year in Singapore. I also had a paper in iClear accepted with other people from Oxford. This was about camera pose localization. So if you have a 3D scene, and if I give you a completely new viewpoint, and if you want to localize that viewpoint with respect to the given 3D scene, that's what we do in this paper. And the main kind of approach, like contribution, was to do this very efficiently and very fast as compared to other approaches. We also have a survey paper, which I think you might find interesting, about LLMs and 3D understanding. So I think, Jamie, you mentioned this reasoning-based sort of idea, and we cover some of those papers here. It's quite an extensive paper, actually. We had about 20 co-authors from ETH Zurich, TU Munich, all these places, and it was a very extensive effort. It took us like 6 months to write this paper, but we have about 50 to 60 papers very carefully surveyed in our survey paper, and you can have a look, to get a good understanding of what's going on in the field. And that's it. Nothing else from my side. If you have any questions, I'm really happy to answer them. But yeah, that's all the slides I had.
Thanks a lot, Yash. Audiences, if you have any question for Yash, please unmute and ask. Yeah, very impressive work, Yash.
Thank you, Abhi.
They're quite interesting, especially the last one. I think I have to read some more about it. This looked quite interesting.
Absolutely. I'm very proud of the demo I had, because it took me like one entire day to make that demo, but eventually it looked quite nice. So.
Yeah, it like highlights the objects that are it's very impressive. Yeah, thank you so much.
Thank you.
Yeah, really, really great work. I think for a short time, right, a couple of years, Yash, you really
Yes.
did so much, and then really, really great work, and for the contribution as well.
Thank you, Jamie. Thank you.
Yeah, and it's also very late at Yash's place, so yeah, I think we can call it a day if there's no more question. Thank you so much, Yash. Once the video is uploaded, I'll let you know. Okay.
Absolutely. Thank you so much for inviting me today.
Yeah, sure. Thanks.
Right. Have a good day.
Thank you.
Yeah.
Bye.
Bye.
Bye.